Computers are binary creatures. They can recognize only two distinct electronic states of electrical charge. These states are identified as 0 and 1, or equivalently false and true, or off and on. Imagine 0 and 1 as the superheroes of compact communication, like yin and yang, representing good and evil in digital realm. In this digital adventure, data takes the form of thrilling sequences of zeros and ones, shaping the destiny of our digital world. So, what is a binary number? It's simply the sequence of zeros and ones. To understand binary numbers or any other number systems, you should first revisit the base 10 system. Wait, hold on. What the hell is a base 10 system? Relax, don't be intimidated by the term base 10. It's just a fancy way of saying good old decimal numbers. The term base refers to the number of distinct symbols that can be found in the numerals. In the base 10 system, there are 10 symbols, numbers from 0 to 9. Binary numeral is a sequence of binary digits called bits. It's also called a base 2 system. Think of bits as a computer building blocks, zeros and ones that they use to build the data castles, aka bytes. Now, pick an arbitrary 5-digit number such as 26,738. You know that the value of this number is 2 times 10,000, 6 times 1,000 plus 7 times 100 plus 3 times 10 plus 8 times 1. Each digit is multiplied by a power of 10. We carry the same ideas into a number system with just 2 digits, 0 and 1. We can use the same principle as we used with base 10, except we will replace base 10 with base 2. Each digit is multiplied by a power of 2. The binary numeral 101, for example, represents the quantity that we write as 5 in decimal, because 101 stands for 1 times to the power of 2 plus 0 times to the power of 1 plus 1 times to the power of 0, which will be equal to 5. To find the value of this binary number, multiply the last digit by 2 to the power of 0, then followed by 2 to the power of 1, to the power of 2, to the power of 3, to the power of 4, to the power of 5, and it will be equal to 53 in decimal. With n bits, we can have 2 to the power of n combination of digits. Thus, with n bits, we can represent the numbers from 0 to 2 to the power of n minus 1. For example, if we have 8 bits, we can represent numbers from 0 to 2 to the power of n minus 1, which are the numbers from 0 to 255.
Huh?
What? Let's analyze this statement for a closer examination. Imagine we possess 2 bits, where n equals to 2. In this scenario, we find ourselves with a total of 2 to the power of n combinations, which amounts to 4 unique possibilities. These 4 possibilities are as follows: 0, 0, 0, 1, 1, 0, and 1, 1. With those bits, we can represent the numbers from 0 to 2 to the power of n minus 1, which corresponds to numbers from 0 to 3. Change each of those binaries to decimal and you'll find out those numbers are 0, 1, 2, and 3. To convert decimal to binary, simply follow those 4 steps. Divide the number by 2. Get the integer quotient for the next iteration. Get the remainder for the binary digit. Repeat the steps until the quotient is equal to 0. For example, let's convert 13 to binary. Divide 13 by 2, and the quotient will be 6, remainder will be 1. And then divide 6 by 2, and you'll find the quotient to be 3, and the remainder will be equal to 0. And again divide 3 by 2, and the quotient will be 1, and also the remainder will be 1. Divide 1 by 2, quotient will be 0 and remainder will be 1. Write those numbers from bottom to top and you will find this number. It's the binary equivalent of 13. Now let's discuss the base 16 system, also called the hexadecimal number system. It's called the base 16 because it uses 16 digits, but there are only 10 digits in the decimal number system. The first 6 letters of the alphabet are used as the next 6 digits. But wait.
Like, what is the point of this? Why do you...
We already have binary numbers to represent data. Look, the hexadecimal number system solves 2 problems. 1. Hexadecimal numbers are very compact and easy to read. Rather than reading this number, it's easier to represent it as this number in hexadecimal. Second, each hexadecimal digit uses exactly 4 bits, making the conversion from binary to hexadecimal easy.
And what does that mean?
In simpler terms, it's like taking 4 binary digits and matching them with one symbol in hexadecimal, making the conversion neat and tidy. Given this hard-to-read decimal number, convert it to hexadecimal, simply follow 4 steps. Step 1. Break it up into 4-bit groups. Step 2. Use this table and replace each 4-bit group by the corresponding hexadecimal number. Put this together and you have the result. If this video helps you out,